So so let me try to motivate this work. So we think that there are 4 major developments in recent macroeconomics. So first, as we've seen also on this conference, most macroeconomic models are heterogeneous agents. And so we try to introduce different types of heterogeneity in terms of assets, for example, capital and bonds, housing, and so on. And also in terms of sources of heterogeneity, like earnings or uncertainty, and so on, right? And so the second development is about introducing uncertainty into macroeconomic models. And this began with the work of Nick Bloom and also Fernandez Villaverde. And at this point, we know how to solve those models of uncertainty, right? So this papers are motivated by the fact that during recessions or during pandemic, we see more uncertainty at both aggregate level and individual level, and it would be kind of important to incorporate this uncertainty into macroeconomic models. So next, so we see more and more people using global solution methods versus perturbation, right? And this is began maybe in 2007, 2009, after the Great Recession, when there was zero low bound. Everyone wanted to account for zero low bound well, right? And after that, so models had financial intermediation, all types of borrowing constraints, inequality constraints, and all these innovations required using global solution methods. And finally, redistribution. This could mean 2 things. From one side, government redistribution, and from the other side, if you have many shocks in the model, they redistribute across different types of agents, right? And so normally, these 4 major developments are introduced in isolation. And so we thought it would be good to put them in one model, in one paper, and see whether it makes a difference, right? So let me start from the model and outline. So we study standard Hank model with wage rigidity. So the reason we consider wage rigidity rather than price rigidity is that, as you know, in the model with price rigidity, you have counter-cyclical profits, right? And so if you want to account well for distribution, wealth distribution, and also different relative relative differences across different agents, so it's important kind of have this side also, right? So that's why we use wage rigidity. So at the household side, we have 2 assets, bonds, liquid assets, and machines, liquid assets. There are 2 borrowing constraints, one for each of those assets. At the household level, we introduce idiosyncratic shocks to both productivity level and variance. And then, as I mentioned, sticky wages. Then at the firm side, so we assume constant return to scale with machines and labor, and then aggregate shocks to TFP level and variance. So we model symmetrically household sector and production sector in terms of uncertainty. So there will be many shocks, right? And then government, we model both fiscal policy and monetary policy. For fiscal policy, we consider progressive income taxation, as is done in his code et al. And for monetary policy, standard Taylor rule with 0 So these are the processes that we use to model levels and uncertainty shock. For example, for the households, eta L of J represents like shock to idiosyncratic level of productivity. And in this first order regressive process, you have this standard deviation which depends on time. When you specify the process for this time-dependent volatility, so it's like first order regressive process, and this shock will be not individual specific, but aggregate, right? So there will be the same shock for all heterogeneous agents, right? Then the same is assumed for aggregate TFP. So you have this time-dependent standard deviation, and then you have a separate process for the uncertainty shock. So all of them are modeled symmetric. So before I explain what we do in this paper, I would like maybe to stress that the literature did things in a slightly different way, right? So for example, if we talk about literature introducing uncertainty, so mostly there's some papers that either consider aggregate uncertainty in representative agent models, or idiosyncratic uncertainty on the production side with representative consumer, right? So there is no like paper that tries to introduce both idiosyncratic and aggregate uncertainty, right? And so there is found these papers about heterogeneous agents in terms of aggregate stochastic output. So then about solving these models with uncertainty, we know from the previous literature that perturbation methods could be problematic, as is argued in Fernandez Villaverde paper. The solution should be at least of order 3, right? And this is kind of already common knowledge. So some papers argue that even for some processes for shocks, you need to go to 4th or 6th order of perturbation. And so this implies that we do need to consider like maybe global solutions to capture all the effects of uncertainty on decisions. Then if you look at Hank literature, so as it was introduced in Kaplan, Mullen, Violante paper, so the common approach is to consider aggregate MIT risk shocks, right? So in this case, you solve model without aggregate TFP shock, and then when you do simulations and draw impulse responses, you add those aggregate MIT shocks. So usually there is no idiosyncratic or aggregate uncertainty. If there is some kind of uncertainty, idiosyncratic, for example, in this paper, you still assume aggregate MIT risk shocks. In some, so when papers try to add uncertainty to Hank literature, mostly this is in the form of MIT shocks. And again, so there is no consistent kind of analysis of both aggregate uncertainty shocks and aggregate risk shocks. And then finally, relation to Hank computational literature. So we've seen a lot of new algorithms for solving heterogeneous agents models, and many of them are based on this Michael Reiter's idea of using local perturbations at the aggregate level and global solutions at the individual level. So here's a list of this novel algorithm. And so the basic issue with these algorithms is that you cannot really consider TFP dynamics over time, right? Because of local perturbations at the aggregate level. And as a result, so you need to focus on MIT aggregate shocks and the low order perturbations for aggregate solutions. And so in this paper, following our previous paper, we address these problems and with AI and deep learning, so that we are able to add aggregate shocks into the solution procedure and solve globally and not using perturbation. So this slide summarizes this previous work with Sergey and Paul Blavinant. And so I wanted to emphasize maybe one of the key features of this algorithm, which I think is very important for heterogeneous agent models, which we called all-in-one expectation. Notice that in the way I specify processes for shocks, they are continuous processes, right? And so if you have many sources of uncertainty, many types of shocks, this technique, all-in-one expectation, is very useful because it allows you to work integrate easily for the case of multiple shocks and heterogeneous agents. So in the model of Crusoe-Smith type. Right? So just to set up notation, so we represent our Hank model as a system of equations which have expectations. The integrand depends on decision function, which is a function of state S. Epsilon is innovation. So we use deep learning. So we parameterize decision function by a deep neural network where phi, which depends on the state and parameters theta that we define by training the machine. And so then in this paper, one of the objectives that we proposed was to minimize the sum of squared residuals, so of equations. So ideally, this should be equal to 0. So in practice, it will not. But while you're doing this, you'll find this vector of parameters theta. And then, as I mentioned, I think it's important if you want to insist on continuous shocks and multiple sources of uncertainty to look for ways to integrate, in particular, this objective function contains expectation and then to the power of 2. Then when you do stochastic gradient descent and you need to compute the gradient of the loss function, and it should be expectation, so you will need to compute expectations, right? And so the idea behind this technique is to say, okay, so according to Jensen's inequality, the square of expectation is not equal to the expectation of square, right? So then you, instead of, let's say, using deterministic integration, what you do, you can draw, instead of one innovation, two innovations, which are independent, represent as a square product of these two integrands evaluated in two innovations, and then collect, since epsilon 1 and epsilon 2 are independent, them outside the expectation. And so that's why it's called all-in-one expectation, because it allows us in the algorithm to collect all shocks, all random variables in the same place. And this is not only innovations, but also random draws of initial conditions of the model, right? So for example, capital in optimal growth model is drawn as a random variable, and if you use this all-in-one expectation operator, then you can put all sources of randomness in one place. And then finally, stochastic gradient descent is essential for this type of algorithm, and the use of PyTorch or TensorFlow simplifies this. So one way that we approach solving Krusell-Smith type of model in this paper and our previous paper is to consider discrete number of agents and then work with so-called true state space rather than a reduced state space. In some sense, it's not completely true state space because we don't consider continuum of agents, but maybe 1,000 of agents. But still, you consider Krusell-Smith method, so it's also simulated not for continuum of agents, but for 1,000 of agents, right? And so in this model, we use in the state space of decision function of agent I, not on the variables of all agents, distributions. And so if you have hundreds of agents, you will have hundreds of state variables. So basically, instead of using aggregate moments, as was originally proposed by Krusell-Smith, so the whole distribution enters the state space. And the way we construct this is to include basically variables of the same agents 2 times, right? Just for convenience, and it proved to work the best. And as a result, you might imagine that it leads to multicollinearity in the regression, right? And so luckily, because of a neural network deals well with ill conditioning by ignoring collinear and redundant variables. So the fact that we add variables of the same agent 2 times does not breaks the iteration procedure.
Can I ask you a practical question? So, like, we simulate a lot of agents. We have a rule of thumb, technically, that you recommend. Like, you know, what is a good number of agents? 1,000, 10,000?
I think it depends on the model. So this model, Hank model, is very nonlinear with more equations, with more neural networks, right? So for Krusell-Smith model, it was not an issue, right? So 1,000 agents, and usually the like bottleneck, let's say, it's like overflow memory. So the computer doesn't have enough memory to generate so many like data points, right? So whatever, it's hard to deal with that. Okay. So this is my model. So let me just mention a few equations. Agent maximizes a discounted sum for utility. It includes some labor or leisure. So we have 2 assets, bonds and physical capital. And physical capital is subject to adjustment cost, which we model exactly as in Kaplan-Maliar. So there is this idiosyncratic productivity shock, which we said also we have risk shock and uncertainty shock. And then there are 2 borrowing constraints. So let me just mention one thing, how this model, which is New Keynesian model, could be different from, for example, the model that was presented today, at the beginning of the day, also OLG model, right? So we know that it's hard to solve a model with more than 1 asset. So 2 is already like a serious complication. And so for new Lausanne model, you cannot really like think of starting from a simple model, including only capital, and then try to add bonds. Because this model has zero lower bound and Taylor rule, right? And so model with capital will not have Taylor rule, right? So it will be like a different model. So there is no nested structure for this model. And that's why it is more complicated in this sense. So this is a formula for adjustment cost. It is designed to match empirically this facts about rich hand-to-mouth, poor hand-to-mouth, and their proportion in the population. Right? The only thing that we know so little about adjustment cost function, we really need the work of the previous speaker to estimate this function, so that we just use the values in our models without trying to just to search for them. Okay, so progressive tax function, which includes parameters tau1 and tau2. The rest of the model is very standard. So you have labor union. So because of wage utility, you have only one Phillips curve. Then you mentioned production function is constant return to scale. So Taylor rule is nonlinear and subject to zero lower bound. So we have monetary policy shock. And these are market conditions. So let me briefly discuss calibration. So when we looked for parameters to be calibrated in the model, so we didn't find a single paper that would estimate both idiosyncratic uncertainty and aggregate uncertainty. Right, so what we did is just to consider separate sources. One paper with the values for idiosyncratic uncertainty, the other paper with aggregate uncertainty. And
I think there is a paper by BOV premature.
Okay, so I'll ask you for the reference. Okay, so thank you. So I will check it. Actually, I don't know how they did it, right? So it's interesting exercise. Sure, okay. Okay, so then maybe it will make it easier. Okay, so then most of the parameters are standard. Again, so we try to match this ratios of hand-to-mouth mentioned in Kaplan and this paper Weiner. We use mostly standard parameters, for example, for tax function from this fiscal paper. And then, as I said, for idiosyncratic shocks, for level type of shock, we use this Auckler et al. For volatility shock, we use the paper by Bayer et al. And then for TFP volatility shock, we use this Fernandez et al. Okay. So before I show my figures with the results, I just wanted to show how this all-in-one expectation operator enters the equations and so why it simplifies the analysis. So I remind that for this heterogeneous agent types of model, three features are important: how to represent the model as a deep learning objective, then all-in-one expectation operator, and how to work with the entire state space. So as was mentioned by the previous speaker, to handle Warren constraint or inequality constraint, we use this function, Fisher-Burmeister function. which converts your Born constraint into some differentiable function. Okay, and so when you write your Euler equation or left side of Euler equation, you represent this in terms of this Fischer-Burmeister function. I maybe say some more about this function. So it, if you look at it, it's actually, if it is written in terms of parameters A and B, because they are restricted in this way, greater than 0 and product is equal to 0, they mimic Kuhn-Tucker conditions. And so if you use this Fischer-Burmeister function, you basically impose Kuhn-Tucker conditions in some differentiable way, which simplifies your life a lot. And so this is how your Euler equation looks like in terms of Fischer-Burmeister function. So this is A and this is B from the previous slide. And so notice that why we need all-in-one expectation operator, because this innovation epsilon, these are shocks, right, is under the square, so you cannot take it out here. And so you need to use, for example, grid for epsilon and then grid for Z and W, so it's just very expensive. But if you kind of combine epsilon without trig and put it outside, it makes your life much easier. So for this particular equation, you just rewrite the Euler equation by introducing this mu expectation. So this term is mu, right? And so and then you add a restriction on mu. So mu is equal to expectation, and as a result, you can put in terms of the previous equation, this epsilons outside. If you draw two innovations, epsilon 1 and epsilon 2, then inside of this expectation, you will have the product of two functions evaluated in these two innovations. And as a result, so you don't need to use deterministic integration or other expensive integration methods, as it directly follows from here. So for Crystal-Smith, it looks similar. So I just wanted to mention that when we solve this model for Crystal-Smith, it's easy because you just need to have one neural network from which you can compute aggregate capital, right? When you have a Hank model, because of more complicated structure, you cannot just use one neural network. You need more neural networks. And so for Crystal-Smith model, when you look at the state space, in terms of our algorithm, it includes capital holdings of each agent and the productivity level of each agent. And then you in addition have this aggregate capital and aggregate productivity as state variables. And so you compute individual capitals by training neural network for L agents, right? And then you find aggregate capital by averaging individual capital. So when we go to Hank model, so things get more complicated. In particular, you will need two neural networks. We use this structure or architecture for neural networks. So one is for aggregate variables. In our case, it's labor and inflation. And then a second neural network for individual variables. So these are shares of consumption, capital, and some multipliers. So in total, you have 3J plus 5 state variables. So if you have 1,000 agents, this will be 3,005 state variables. and then you can, yeah. Yeah, and so then you can sequentially recover all your variables if you train both neural networks for aggregate and individual variables. So this explains how to do it. Okay, so let me show some results. We'll look at distributional predictions and also at impulse responses when we consider two types of shocks, idiosyncratic uncertainty shocks and aggregate uncertainty shocks. So basic idea when we started, we wanted to see which one is more important, right? So we know that during recessions, we can observe both types, idiosyncratic uncertainty shocks and aggregate uncertainty shocks. But empirically or quantitatively, which one in the model is more important, right? Okay, so these are model generated statistics for wealth consumption and net income Gini. So in the data, we have wealth Gini coefficient equal to 0.79. So this model can generate high degree of wealth inequality easily, right? So we know the Crusoe-Smith model, unless you introduce preference shocks, discount factor shocks, like cannot really match wealth Gini. So this is not true for this Hunt model with distribution. So consumption Gini and the net income Gini are in line how it should be in the data. They are much lower than wealth Gini. And then we do impulse responses following this Besseran and Potter paper. So the idea is that since we have many shocks, you cannot really shut down all of them to draw impulse responses, right? So what you should do is to use your solutions with all the shocks. And then when you plot impulse responses, all the shocks should be there as well. And so you should make a variation for one shock in one period and compare to series. And this is what this paper suggests, not for this particular type of exercise, not for structural DSG models, but in a different context. But we thought that it's useful here as well. And so the idea is to draw two series, like sequences without innovation and with innovation. So they differ only in the first period shock, right? And then for the rest of the periods, all the shocks are the same, and then we compare relative responses. And so this is done for TFP uncertainty, individual uncertainty. We need to make many draws with different initial conditions. And then for each initial conditions, there are multiple draws of innovations. Then these results are presented for 200 pages. So what we found in general, thank you. So uncertainty shocks are more important than aggregate shocks, right? And so you see orange line is individual uncertainty, blue TFP uncertainty. So on the impact of shock in one period, so again, remember, so all the shocks are there, just only one small shock in period 0. In this case, if it is orange, individual uncertainty shocks differs by one standard deviation, right? And the rest of the series is the same. So this is the impact of this change of innovation in period 0. So on the impact, you see, well, this is average wealth, it decreases, but then it goes up. For TFP uncertainty, we don't really see much effect of TFP uncertainty shock. So is this result surprising, right? I'm not sure how to kind of even in line with what Chris was saying yesterday, so models should have uncertainty shock or volatility time dependent, right? But on the other hand, this is like a second shock to the second moment, right? So you don't really kind of expect the effect to be very large. Because it's not first
you
order.
don't expect it to be
Okay,
large.
so at least this is what we have here. So
You
we
don't
have
expect
a
it.
bigger effect of individual uncertainty than aggregate, and even this is not very big, right? Then this is true for all other variables, like wealth Gini, for example, for this individual uncertainty, first increases and then goes down. All these changes happen because of different rates of return on capital and bond. Capital is subject to adjustment cost, while bond is not, right? So that's why capital mostly is held by wealthy households, which can afford to pay all this extra cost to modify the portfolio, right? Then this is how labor earnings look like, net income Gini increases. So there is an increase in income inequality due to individual uncertainty and not due to aggregate uncertainty. And then at the qualitative level, the difference between TFP uncertainty and idiosyncratic uncertainty is the effect on, let's say, output, capital, consumption. So if you have an aggregate uncertainty shock, output goes down, capital goes down, consumption goes down. While if you have individual uncertainty shock, so output goes up, capital and consumption go up. And so in conclusion, I just want to mention this general result that it looks like the response to individual uncertainty shocks is much larger than the response to TFP uncertainty shocks. In particular, individual uncertainty shocks increase income inequality and leads to a persistent increase in wealth following an initial reduction. So we want to extend the model by introducing correlation between individual and aggregate uncertainty. And so we try to compare our results with the one if we use your paper, right? So one thing that we found is that when we have so many shocks, right? We have like 4 only for uncertainty, and then we have multiple shock and so on. So we should discretize. Discrete. It's not. Yeah, it's not working. That's why I was trying to emphasize all in one expectation operator, because it allows you to work with continuous processes, right? And it makes it possible, if you're interested in many shocks, to solve models with many shocks. And so we're still working on the effects of fiscal inequities.
I'm sorry, I missed the first part. I was jet lagged and I was going to go to sleep, so I went to my hotel to go to sleep instead of in front of me. So do you have transitory and permanent shocks at the individual and aggregate data level, or what are they?
In our previous version, we did have, right? So here we did not. I don't know. So we thought we have already many shocks, right? So we still are going to distinguish for each of them transitory and permanent, right? Then there will be even more shocks. I mean, maybe this is.
So my favorite statistic on this is that you estimate exactly the same process for permanent shocks at the micro and the macro level. In the micro shocks, the variance is 100 times larger. And so the possibility of a shock to the level of idiosyncratic permanent is
Okay,
very likely to be
Okay.
much bigger.
thank you so much for this comment. So we will then show introduce.
Another question?
So how should we understand, this opposite effect of aggregate uncertainty and integer uncertainty on the aggregate cost?
This is preliminary result, okay, so, and this is quantitative result, okay. So how should we understand? Chris Norbert, who is my student at DSE, he's very talented at giving intuition about anything. So you can really find a nice intuition why one variable goes up and one variable goes down. Will it be true in this highly nonlinear, very kind of complicated model? I don't know. So I think maybe yes, maybe not. But it's kind of important. But at this stage, we're still trying to work on the details. Thank you.
Thank you very much.